technically speaking, cold actually does not exist.
Right, it's a physical impossibility.
Exactly. I mean, there is no tangible substance or, molecular particle that we can point to and say, yes, that is cold.
In physics, there is really only heat and, well, the absence of heat.
Yeah, but think about it. We interact with this illusion of cold every single day, right? You buy a big insulated box for your kitchen, plug it into the wall, and just expect it to somehow manifest this non-existent stuff so your milk doesn't spoil.
Or you just expect your air conditioner to conquer a scorching July afternoon with, like, the push of a button.
Right, but when you bypass the buttons and actually look at the mechanics happening behind the hum of those machines, you realize you aren't summoning cold at all.
No, not even a little bit.
You are witnessing this beautifully orchestrated, actually incredibly aggressive manipulation of thermodynamics. And that is exactly what we are exploring with you today. Welcome to another deep dive.
We have some truly fantastic source material guiding us today, too.
We do, yeah.
We are looking at a set of university-level lecture notes on thermodynamics. Specifically, it's Lecture 4, authored by Richard Love from Massey University over in New Zealand.
And our mission for you today is to completely demystify the standard refrigeration cycle.
It's going to be a fun one.
Oh, absolutely. We're going to break down the actual physics of how heat is forcibly extracted from a cold space and dumped into a warm space, which totally defies what heat naturally wants to do.
Right, it's like pushing water uphill.
Exactly. And we'll explore the seemingly impossible math of how these systems output vastly more energy than they actually consume.
Which sounds like magic, but it's just really good engineering.
And finally, we will discover how taking this exact same mechanical loop and simply flipping our perspective gives us one of the most powerful sustainable heating solutions in modern industry.
Okay, let's unpack this.
Yeah.
Because before we can analyze the performance multipliers, we really have to dissect the anatomy of the cycle itself.
Yeah, we need to understand the mechanism of the loop. That loop is the foundation of literally everything we're discussing.
The Massey University notes lay this out by dividing the standard vapor compression refrigeration cycle into 4 continuous stages.
4 stages, got it.
It's a closed circuit, right? A specialized fluid, the refrigerant, just circulates endlessly through this circuit. And the core challenge this fluid is tackling is the second law of thermodynamics.
Right, the second law, which basically dictates that thermal energy naturally flows down a temperature gradient. It wants to flow from hot to cold.
Always.
Like if you leave a hot cup of coffee on your desk, the thermal energy dissipates into the cooler room. Heat never spontaneously flows from a cold object to a hot object.
Spontaneously being the totally operative word there.
Right.
Because to force heat to travel up that temperature gradient, to move it from the cold interior of a fridge out into a warm kitchen, well, that requires deliberate mechanical intervention.
And the first stage of that intervention happens in the evaporator.
Exactly. This is the heat exchanger located inside the space you are actively trying to cool down.
The notes detail that the refrigerant enters this evaporator coil as this low-pressure liquid vapor mixture sitting right around 0 degrees Celsius. But what really stands out to me is why that pressure matters so much.
Oh, it's everything. Pressure dictates the boiling point. I mean, we are so accustomed to water boiling at 100 degrees Celsius.
Right, everyday life.
But that's only true at standard atmospheric pressure. If you drop the pressure, the intermolecular forces holding the liquid together weaken.
Oh, making it easier to boil.
Exactly. It takes significantly less thermal energy to induce a phase change. So the refrigerant is specifically chosen and maintained at such a low pressure that its boiling point drops to 0 degrees Celsius.
Meaning that the air inside your refrigerator, which might be sitting at, a brisk 4 degrees Celsius, is actually hot enough to act as a furnace for this refrigerant.
That's a great way to look at it, actually.
Yeah.
The 4-degree air transfers its thermal energy into the 0-degree liquid refrigerant, and this causes the refrigerant to boil.
Just from the ambient air in the fridge.
Yeah. Now, during a phase change from liquid to gas, the temperature of the fluid doesn't actually rise.
Wait, really? It boils but doesn't get hotter?
Right. Instead, it absorbs what we call latent heat. It's soaking up the thermal energy required to physically pull its molecules apart into a vapor.
Ah, got it.
And this absorbed heat is referred to in the thermodynamic equations as Qin.
Okay, so the refrigerant has absorbed Qin. It boils into a low-pressure vapor, effectively trapping the thermal energy from your groceries inside its newly expanded gaseous state.
Yep.
But now the heat is still stuck inside the box, which leads us to component number 2, right? the compressor.
The absolute heavy lifter of the system. This is the only component in the entire loop that requires an active input of electrical energy.
Which the notes denote as W for work.
Correct. The compressor takes that low-pressure vapor carrying the latent heat from the fridge, and it aggressively reduces its volume. It just squeezes it.
And mechanically, I mean, when you force a gas into a significantly smaller volume, you are doing work on those molecules.
A lot of work.
You're increasing their kinetic energy, which causes them to collide with each other far more frequently and with much greater force.
And macroscopically, those violent molecular collisions manifest as a massive spike in temperature and pressure.
So it gets really hot.
Very hot. The fluid entered the compressor as a cold, low-pressure vapor, but it exits as a highly pressurized, superheated vapor.
Wow.
Its temperature is now significantly higher than the ambient temperature of the room your refrigerator is sitting in.
Which perfectly sets up the third stage, the condenser. These are the coils you typically find, like hidden on the back or underneath the appliance.
Yeah, the ones that are always covered in dust.
Exactly. So we've taken the thermal energy from inside the fridge, and through the brute force of the compressor, we've jacked its temperature up so high that it is now hotter than the kitchen air.
And because it's hotter than the kitchen, well, the second law of thermodynamics is suddenly working in our favor again.
Right, hot to cold.
Heat spontaneously flows from hot to cold. The superheated vapor radiates its thermal energy out into the ambient air of the room. And this rejected thermal energy is our Q out.
So as the refrigerant rejects that heat, it loses the kinetic energy required to maintain its gaseous state.
Exactly.
It undergoes another phase change, condensing back down into a high-pressure liquid, settling at around 40 degrees Celsius.
Yep.
So it has successfully smuggled the heat out of the fridge and dumped it into your kitchen.
Mission accomplished.
But we have a problem. We now have a 40-degree high-pressure liquid. To keep the loop going, we need a 0-degree low-pressure liquid to feed back into the evaporator.
And that is the job of the fourth and final component, the expansion valve.
Okay, I want to try an analogy here just to see if we can visualize the full system without getting completely lost in the phase states.
Let's hear it.
Is it kind of like a sponge?
Yeah.
Like, imagine the thermal energy is water. The evaporator is a dry sponge sitting inside the fridge, just passively soaking up the water. The compressor is an arm that physically picks up the heavy, wet sponge. The condenser is a hand tightly squeezing that sponge, physically forcing the water out into the kitchen.
I like this.
And the expansion valve is the hand letting go, fluffing the dry sponge back up so it's ready to absorb water again.
It's a really good structural visualization. The soaking, moving, squeezing, and releasing.
Yeah.
But since our listeners know their way around an engine room, let's look at the actual thermodynamic mechanism happening at that fluffing stage.
Because it's not quite as passive as letting go of a sponge, is it?
Not at all. What's fascinating here is the isenthalpic expansion occurring in that valve.
Isenthalpic meaning the total enthalpy or the total heat content of the fluid remains constant.
Exactly. The expansion valve is essentially just a deliberate bottleneck. It's a tiny orifice.
Okay.
The high-pressure liquid is violently forced through this microscopic opening into a much larger, lower-pressure chamber. During this throttling process, the fluid doesn't do any mechanical work, and it happens so incredibly fast that no heat is exchanged with the outside environment. But because the pressure drops so rapidly, a small fraction of the liquid instantly flash boils into a gas.
And boiling requires energy.
It requires latent heat. And since no heat can enter from the outside, the fluid that flashes into a gas actually steals the necessary thermal energy from the remaining liquid.
Oh, wow. It cannibalizes its own heat.
It totally does. It converts the fluid's own sensible heat, the heat you can actually measure with a thermometer, into the latent heat of vaporization.
Right.
This internal energy theft causes the temperature of the remaining liquid to absolutely plummet. It drops violently back down to a 0-degree, low-pressure state, fully prepared to enter the evaporator and begin the cycle anew.
That is just a brilliant piece of engineering. I mean, it's an endless cycle of manipulating pressure to hijack the phase states of a fluid.
It really is. And it all culminates in the foundational thermodynamic equation provided in the Massey notes.
Right, the math.
The total work we input at the compressor, RW, equals the heat we reject at the condenser, Q out, minus the heat we absorbed at the evaporator, Q in.
Or, to rearrange it for clarity, Q out equals W plus Q in.
Exactly.
The thermal energy we dump into the kitchen is the exact sum of the electrical energy we use to compress the fluid, plus the thermal energy we scooped out of the refrigerator.
Spot on.
Now that we understand the mechanics of how this heat relocation program operates, it raises an obvious question.
Which is?
How do engineers measure if this system is actually operating efficiently? I mean, we're putting electrical energy in, and we're moving thermal energy around. How do we grade the performance?
Well, in thermodynamics, we evaluate this using a metric called COP.
Okay.
That stands for the coefficient of performance.
Mm-hmm.
The lecture notes define this using a beautifully elegant golden rule. COP is simply defined as what we want divided by what we pay for.
I really appreciate the pragmatic engineering approach there. So if we apply that to our refrigerator, what we want is the cooling effect. We want the heat to be absorbed by the evaporator. That's our QN.
Right.
And what we pay for is the electrical energy required to run the compressor. That's our work, or W.
That is correct. For a standard refrigeration cycle, the COP is calculated as QN divided by W, the thermal energy removed divided by the electrical work put in.
I have to push back on this terminology, though.
Oh, how so?
When we evaluate the performance of almost any other machine, like an internal combustion engine, a gas furnace, an LED light bulb, we talk about its efficiency.
True.
And efficiency is strictly bound by the first law of thermodynamics, the conservation of energy. You absolutely cannot get more energy out of a system than you put into it.
Obviously not.
The theoretical maximum efficiency of any machine is 100%. But when you look at the COP values detailed in these lecture notes, they are consistently greater than 1.
Yeah, they are.
They are reporting COPs of 3, 4, sometimes even higher. A COP of 4 essentially implies an efficiency of 400%.
Right.
How is the system supposedly generating 4 units of energy for every 1 unit we put in? We can't just ignore the first law of thermodynamics.
It's an excellent challenge, and honestly, it is the most common conceptual hurdle when people are first dealing with these systems.
It just feels wrong.
The critical distinction is that a refrigeration cycle is not generating thermal energy from scratch.
Okay.
If you analyze a standard electric resistance heater, like a space heater or the coils in your toaster, you are directly converting electrical energy into thermal energy.
Right.
And due to the first law, 1 unit of electrical energy yields exactly 1 unit of thermal energy. That is 100% efficiency, a COP of 1.0.
Right. The energy is just changing forms from electrical to thermal, but the absolute quantity remains identical.
But our refrigeration cycle is not converting electricity into the heat we care about.
It's not.
No, it is utilizing electricity strictly to perform the mechanical work of compression. The system is a pump. We are paying the utility company to operate the compressor, which moves the fluid, which transports the heat. The vast majority of the thermal energy we are moving, the QN, was already there. It was just sitting in the ambient environment. We didn't create it, we just gathered it.
I understand now. We are essentially engaged in energy arbitrage.
Exactly.
We aren't manufacturing the commodity, we're just paying the transportation costs to relocate it.
Precisely. The COP can vastly exceed 1.0 because the useful output is the thermal energy we gathered for free from the environment, while the input we evaluated against is only the small mechanical toll we paid to move it.
That makes so much more sense.
We aren't violating the conservation of energy. The total energy remains totally balanced across the entire system boundary. We're simply exploiting a thermodynamic loophole by spending high-grade electrical energy to herd a massive amount of low-grade ambient thermal energy.
That reframes the entire concept of heating and cooling, which leads us perfectly into the third major section of the lecture notes.
Yes.
If this mechanical loop is so incredibly adept at gathering and moving thermal energy out of a space, what happens if we decide that the waste heat coming out of the condenser is actually the commodity we want?
We flip the script. If we shift our engineering perspective, the exact same mechanical loop, utilizing the exact same 4 components, transitions from being a refrigerator into being a heat pump.
So instead of pointing the evaporator at the space we want to cool, we point the condenser at the space we want to heat.
Exactly. In a heat pump scenario, our definition of what we want fundamentally changes. We no longer care about the cooling effect, the QN. What we want is the heating effect. We want the thermal energy being fiercely rejected by the condenser, the Q out.
And the Massey notes make it very clear that this technology isn't just for, keeping residential living rooms cozy in the winter. On an industrial scale, heat pumps are absolute behemoths.
No, they're massive.
The notes cite instances where they are utilized to heat water or air up to 100 degrees Celsius to drive major drying and sterilization operations in manufacturing plants.
And the industrial scale is where the math behind the COP cruelly shines. Let's look at how the performance equation shifts when we operate the cycle as a heat pump.
Okay.
Remember the golden rule. COP is what we want divided by what we pay for.
Right.
For a heat pump, what we want is Q out. What we pay for remains the work, W. So the COP of a heat pump equals Q out divided by W.
But we established earlier with our energy balance equation that Q out is simply the sum of the electrical work we input, W plus the free thermal energy we gathered, Q.
So if we substitute that into our equation, the COP of a heat pump becomes W plus Qn, all divided by W.
Okay, tracking.
If we simplify that fraction algebraically, we get 1 plus Qn divided by W.
And wait, Qn divided by W is the exact formula for the COP of the refrigerator.
Yep.
So the mathematical COP of a heat pump is literally just 1 plus the COP of the refrigerator.
It is a stunningly elegant derivation. When you run the system as a heater, you get 100% of the electrical energy you paid for converted directly into heat.
Which accounts for the 1 in the equation.
Because the heat from the compressor's mechanical friction ends up in the fluid anyway. Plus, you get all the free thermal energy the system pumped in from the outside environment.
Let's ground this abstract math with the specific real-world industrial example provided in the Massey University notes, because walking through the numbers step by step is super illuminating.
Sure.
Imagine a large-scale dairy processing facility. They have a single massive vapor compression system running.
Okay.
On one side, the evaporator is chilling water down to 10 degrees Celsius for cold storage. On the other side, the condenser is generating hot water at 50 degrees Celsius for pasteurization or cleaning.
Let's track the energy flowing through that plant. Let's assume we input 250 kilowatts of electrical work to drive the central compressor.
Okay, 250 units of electrical input. And let's say the evaporator side absorbs 1,000 units of thermal energy from the water to chill it down to 10 degrees.
Got it.
So our refrigeration COP is what we want, 1,000 units of cooling divided by what we paid, 250 units of work. 1,000 divided by 250 gives us a refrigeration COP of 4.0.
For every kilowatt of electricity purchased, the plant gets 4 kilowatts of cooling power.
Right.
Now, trace the energy to the heating side. The thermal energy rejected by the condenser into the hot water is the work we put in, the 250, plus the heat we gathered from the chilled water, the 1,000.
Okay.
So Q out is a total of 1,250 units of thermal energy.
Which means our heat pump COP is what we want, 1,250 units of heating divided by what we paid, 250 units of work.
And the math works out perfectly.
1,250 divided by 250 is exactly 5.0. Just as the algebraic derivation predicted, it is 1 plus the refrigeration COP.
Exactly.
The factory pays for 250 units of energy, but they successfully apply 1,250 units of heat to their processes. The economic advantage over burning natural gas in a traditional boiler is just staggering.
It is an incredible performance multiplier.
Well,
Here's where it gets really interesting. I caught this detail in the notes, and it fundamentally shifted how I view industrial energy management.
no.
Because in that dairy facility, they don't just need heating or cooling, they actively require both simultaneously.
Right.
They need the 10-degree chilled water for storage, and they simultaneously need the 50-degree hot water for sanitation.
This is the concept of simultaneous heating and cooling, where the system transcends being categorized as just a refrigerator or just a heat pump.
Right. If the factory utilizes both the chilled water and the hot water streams, then the what we want variable in our golden rule expands to encompass both outputs.
So true.
We want the 4,000 units of cooling from the evaporator, ND. We want the 1,250 units of heating from the condenser. Our total useful output is 2,250 units of strict temperature control.
And crucially, what we pay for hasn't changed at all.
Nope.
It is still just that initial 250 units of electrical work driving the singular compressor at the heart of the loop.
So if we calculate the efficiency of the entire integrated system, 2,250 units of combined useful output divided by the 250 units of electrical input, that yields a hybrid COP of 9.0.
It's mind-blowing.
The facility pays for 1 unit of electrical energy and extracts 9 units of highly valuable thermodynamic work from the machinery.
It really highlights a vital paradigm shift in engineering. By understanding the intricate enthalpy states of a fluid, and by treating thermal energy as a physical resource to be transported rather than a fuel to be consumed, industries can unlock massive, compound multipliers in their energy efficiency.
So what does this all mean for you, the listener? We have mapped out some pretty complex thermodynamic terrain today.
We covered a lot of ground.
We analyzed the fundamental mechanical loop, the evaporator exploiting low pressure to boiling refrigerant and absorb latent heat, the compressor doing the violent mechanical work to elevate the pressure and temperature, the condenser rejecting that thermal energy to the ambient environment, and the expansion valve utilizing the Joule-Thomson effect to plummet the temperature and reset the cycle.
We established the boundaries of the first and second laws of thermodynamics, proving that we aren't magically creating energy out of the ether.
Right.
We are simply employing a highly optimized electrically driven pump to relocate existing thermal energy against its natural gradient.
And we learned that by merely shifting our operational perspective, this cooling technology becomes a heat pump, a system capable of delivering simultaneous industrial heating and cooling with a hybrid cup that makes traditional combustion boilers look downright archaic.
Truly archaic.
So the next time you hear the faint hum of the refrigerator in your kitchen, you aren't just listening to a mundane box keeping your milk cold. You are listening to a relentless, incredibly sophisticated heat-transporting machine manipulating phase states and exploiting the laws of physics right there in your home.
It truly is a triumph of modern engineering. However, if we pull back and connect these localized systems to the macro-level energy grid, the massy source material leaves us with a final, rather provocative thought regarding the ultimate sustainability of this technology.
Right. The lecture notes explicitly highlight that a heat pump's primary environmental advantage is that it utilizes electricity to facilitate the heating rather than burning fossil fuels right there on site.
Yeah.
But that advantage only holds true if the electrical supply powering the compressor is itself generated sustainably.
Exactly. The final section of Lecture 4 pivots to examine traditional power cycles, specifically the Rankine cycle utilized in major coal or natural gas power plant.
Okay.
If you analyze the thermodynamics of a traditional power plant, it operates almost as the exact inverse of our highly efficient heat pump.
Wait, how so?
In a power plant, they combust massive quantities of fossil fuel in a boiler to create high-temperature, high-pressure steam. They run that steam through a turbine to generate the electrical work. But to reset their cycle, they have to reject a staggering amount of waste heat into the environment through their own massive condensers, often utilizing cooling towers or adjacent rivers.
Let me make sure I'm tracking this. In a traditional power plant, what they want is strictly the electrical work. But because they are operating a thermal engine, they are bound by Carnot efficiency limits, meaning they inevitably lose a massive percentage of their thermal energy to the atmosphere as completely wasted heat.
Yep.
But in our residential heat pump, we use that electrical work to gather thermal energy.
Precisely. And the thermal efficiency of those traditional power plants is often hovering around a mere 35 to 40%,
Wow, that's low.
which raises a critical systemic question for you to mull over. If we are installing incredibly efficient COP4 heat pumps in our homes, but we are plugging them into a macro grid powered by highly inefficient thermodynamic power cycles.
Oh, I see where you're going with this.
Cycles where we burn fuel to create heat, lose 60% of that heat to the atmosphere just to generate a small amount of electrical work, send that work miles down a transmission line just so our local heat pump can use it to gather heat once again.
Are we actually achieving a net reduction in energy consumption on a global scale? Or have we simply shifted the thermodynamic inefficiencies further up the power grid, hiding the wasted heat behind the smokestacks of a power plant miles away?
It is the ultimate thermodynamic shell game.
It really is. And it proves that evaluating energy efficiency requires looking far beyond the boundaries of a single appliance. But hey, until the entire grid is optimized, at least you now have a comprehensive understanding of exactly how the machinery in your kitchen is bending the laws of physics to keep your groceries cold.